integral representation for Lerch Transcendent function. A few hours ago, I just realized that in my channel there was a playlist called Lerch Transcendent function, but over there wasn't really any like sum definition or integral definition and such things about this function, right? So I thought of why not making this video so that the playlist might seem a bit complete, right? For the sake of completion. And then yeah, so that's why I planned on making this video. And then yeah, we'll basically prove the integral representation, and we consider the sum representation as the definition of Lerch transcendent function. And yeah, and one of the reasons that this function is important is because this function can actually generalize a lot of many functions like Horowitz zeta, polylogarithm, Riemann zeta, Dirichlet eta, Dirichlet beta, Legendre chi, inverse tangent, polygamma, Clausen function. All these functions can be generalized by the Lerch transcendent function, and like the properties that belongs to Lerch transcendent will automatically be the properties of all the other functions, right? So that's why it's actually powerful, right? And yeah, so first of all, the sum definition is kind of trying to generalize the polylogarithm function, right? Because also for the polylogarithm function, when we have, let's say, li s of z, it was sum from n equals to 1 to infinity of z to the power n times n to the power s, right? So over here, we are trying to make the sum go from 0, and also we are trying to add a variable over here. So it's sort of generalization of the polylogarithm in like in the first perspective, right? And this is basically a function of g, s, and a, and it's defined as sum from n equals to 0 to infinity of g to the power n by n plus a to the power s. So there's definitely some restriction on z on what it can be, because the sum doesn't really converge for any z, right? So z can just have some specific values, and for those this converges, and that's now if it converges, it can be like seen as a function, and that's Lerch transcendent function, right? And yeah, so in this video we are going to prove that this integral representation also gives Lerch transcendent function, right? Okay, so how do we go on proving this? Okay, first of all, you see that there's this form like 1 by 1 minus something, this form, right? So if you have this form, you always use like infinite geometric series, right? And also, we are gonna like assume that the g is such that uh, this modulus of this thing is less than 1, right? So yeah, we can define z. I mean, we can just restrict z to be such number, right? And if that's the case, um, this will be integral from 0 to infinity e to the power s minus 1 e to the power minus a t, sum from n equals to 0 to infinity g to the power minus t to the power n, right? And then also there's this dt. And then we have 1 by gamma of s. Now I can take all this constant inside the sum, and the integral and sum will exchange it, right? So t to the power s minus 1 e to the power minus a t g to the power n e to the power minus n t dt. Again, now g to the power n is just constant for the integral, so I can actually take that out, and this becomes g to the power n times integral from 0 to infinity of t to the power s minus 1 e to the power minus of a plus n t dt, right? Now we see that this is actually just Laplace transform of t to the power s minus 1, right? So if we use the formula of the Laplace transform, this becomes, again, there are some restrictions on a plus n, because a plus n has to be positive number. But yeah, like we know n is greater than or equals to 0, so that definitely gives some restriction on a, right? But I will just assume that restriction is fulfilled. And then in that case, this will be, and yeah, even if it's not, like we can just maybe do some analytic continuation such stuff. But yeah, we won't really worry about that over here. So and number this one becomes gamma of s by n plus a to the power s. right? And now actually this gamma of s is just a constant for the sum in the n domain, right? So this becomes gamma of s by gamma of s, sum from n equals to 0 to infinity, g to the power n by n plus a to the power s, right? So this cancels out, and we know that this thing over here is the Lerch Transcendent function of g, s, and a. And that proves the thing that we are trying to prove. So that's how this integral representation can be proved. You can actually even go backward, like if you know some of these integrals, like Laplace transform of like like e to the power s minus 1, and then these things. But yeah, we prefer to go in the easy way, and then we just used the integral to get to the definition. So that's how we prove it, and I definitely believe like knowing this form could be helpful while solving integrals, right? And then because now after you have this function in Lerch transcendent form, maybe you can do some operations, and then again simplify it to some other simpler functions like polylogarithm, polygamma, and such functions. So yeah, it could be pretty helpful, and then I hope this integral representation helps. And so yeah, that was all for today. Hope you enjoyed the video. Thanks for watching, and I definitely look forward to seeing you in the upcoming videos too. And guys, thank you so much for the love in the recent videos. Yeah, I look forward to that.